Hello everyone. Now I will introduce our research work about malicious encrypted traffic detection. Existing related approaches need to be trained with many samples. It's a critical problem to how to train a deep learning model using only a small number of samples to detect new classes of malicious encrypted traffic. We propose a few short malicious encrypted traffic detection approach based on Model-Agnostic machine learning. In our approach, we need to pre-process the traffic data firstly. We convert the raw traffic in PCAP format into two-dimensional grayscale image. In first step, we split the continuous raw traffic into discrete traffic units. In second step, we randomize each section's IP address and MAC address, and then remove some duplicate and empty data. This data is generated by slice operation, which can interfere with the model's training. In the third step, we modify the length of all sections to 784 bytes uniformly. Then the data with the same length is converted into two-dimensional grayscale images. Images in PNG format are the output of the last step. 1 byte in raw traffic represents a 1 pixel value in the grayscale image. After data pre-processing, now I introduce our method called FMATD. FMATD consists of a machine learner and a basic learner. The machine learner is MAMO, and the basic learner is deep learning model CNN. The machine learner consists of a meta training phase and a meta testing phase. Few short traffic detection aims to train basic learner that can adapt to new malicious traffic with only a few trained data and parameter iterations. To achieve this, an optimal set of initialization parameters is learned during the meta training phase by training the basic learner through a few gradient descent steps. In the meta testing phase, new malicious encrypted is detected and classified by the trained basic learner. We use MAMO to train CNN with only a few training samples to learn an optimal set of initialization parameters. MAMO is a high-level cross-task learning strategy that can find an optimal set of initialization parameters for deep learning model, so that the model with this initialization can quickly adapt to a new task only using a few samples. During meta training, multiple tasks are sampled from the dataset D, and the model is trained with key samples from this task to obtain its parameters theta. Then the model is tested on the new samples and update the parameter theta by gradient descent. The parameter theta obtained at this point is highly sensitive to the new task, and it is used as the initialization of the model, which can make the model adapt to the new task quickly with only a few samples. This is FMATD. In order to prove the validity of the method FMATD, we set up two experiments, one to verify the validity of FMATD, to detect malicious encrypted network traffic, and the other to verify its ability to detect new malicious encrypted network traffic using only a few training samples. The experimental results show that when the training set has a large number of samples, the two-class classification accuracy of FMATD reaches 99.8%, which was higher than that of the CNN. FMATD also has a multi-classification accuracy of 98.5% on the CNC and MEL 2017 dataset. The experimental results demonstrate that our approach has the same good detection capability as the existing state-of-the-art approaches. As we can see, our method FMETD works pretty well with the best method. In addition to enabling the detection of malicious encrypted traffic, when the training set contains a large number of labeled samples, our approach can quickly detect new class malicious encrypted traffic with only a few samples. First, we did the experiments on the firmware 1-shot and firmware 5-shot setting on the RSCX VPN 2016 dataset. For the 20 classes of traffic data, we randomly selected 12 classes of them as the set of the support set, 4 classes as the validation set, and the remaining 4 classes as the test set. Each class containing 20 integrity-secured images. As can be seen from the table, RF, LSTM, CNN don't detect new malicious encrypted traffic well with only a small number of samples. The multi-class classification accuracy of FMETD was 94.3% on the firmware 1-shot settings on the dataset, and the firmware 5-shot 97.9%. We did another experiment with the CIC and Mail 2017 dataset. For the 22 classes of malicious data in the dataset, we selected 23 as the support set, 8 as the validation set, and the remaining 11 as the test set, each class containing 33 grayscale images. When the setting was changed to firmware 5-shot, the accuracy of FMETD increased to 97.9%, and in firmware 10 shots, the accuracy reached 97.8%. FMETD achieves efficient and accurate detection of new classes of malicious encrypted traffic, which is invisible in the training phase when there are only a few labeled traffic. This demonstrates the strong generalization of FMETD. In FMETD, we convert the raw traffic data into grayscale images for feature extraction and malicious traffic classification. Only the special features of the traffic are used in this process. In future work, we will research how to add these temporal features in our few-shot learning approach. Use RNN to replace the CNN model to improve FMETD. That's all. Thanks for your listening.